When we think of NASA, our minds instantly soar. We picture rockets, we imagine astronauts walking on the moon. We dream of missions to distant Mars and beyond. Yet there is another frontier, equally vast, equally mysterious, right here on Earth. This is our planet's deep ocean. NASA, with its expertise in building robust systems for extreme environments, finds a unique challenge and opportunity here. Exploring this inner space helps us understand our own planet more profoundly. It also prepares us for the daunting task of exploring other ocean worlds in our solar system. NASA's involvement is an expansion of its commitment to explore the unknown. So let us embark on this journey. To explore any new frontier, one must first have a map. The deep ocean, for centuries, was largely a blank space on our global charts. Early mariners could only guess at its depths using weighted lines dropped overboard. The true nature of the seabed remained hidden from view. The advent of sonar technology in the early 20th century began to change this. By sending pulses of sound downwards and measuring the time it took for the echo to return, scientists could begin to paint a picture of the ocean floor's topography. Modern underwater mapping technology has become incredibly sophisticated. Satellites can measure minute variations in sea surface height, indicating the presence of large underwater features. Ships equipped with multi-beam echo sounders can create wide swaths of high-resolution seafloor maps. Autonomous underwater vehicles, or AUVs, can dive deep, systematically scanning areas with even greater detail. Despite these technological leaps, a staggering portion of our ocean floor remains unmapped with this high level of detail. Detailed maps are crucial for understanding ocean currents, predicting tsunamis, managing resources, and identifying unique habitats. The deep ocean is a realm of extremes. At the bottom of the Mariana Trench, pressure is over 1,000 times greater than at sea level. Temperatures can plummet to near freezing, or skyrocket to hundreds of degrees Celsius near hydrothermal vents. These conditions are profoundly hostile to life as we typically know it on the surface. Yet, it is precisely these harsh environments that make the deep sea such a compelling analogue for conditions we might find on other planets and moons in our solar system. Think of Jupiter's moon Europa or Saturn's moon Enceladus. Scientists believe these icy worlds hide vast liquid water oceans beneath their frozen crusts. By studying life around Earth's hydrothermal vents, NASA scientists can develop strategies and technologies for searching for life in these extraterrestrial oceans. Deep-sea environments also serve as crucial testing grounds for robotic systems destined for space. The challenges of operating a rover on Mars share similarities with operating a remotely operated vehicle, or ROV, in the deep ocean. Practicing deployments and troubleshooting problems in the deep sea provides invaluable experience for future space missions. The isolation and confinement experienced by teams operating in remote deep-sea locations can simulate aspects of long-duration space travel. Studying the psychological and logistical aspects of deep-sea expeditions can offer insights into crew dynamics, mission planning, and habitat design for space exploration. The deep ocean is a practical laboratory, helping us understand how life might persist in the harshest corners of our solar system. NASA's commitment to understanding extreme environments fuels specific missions into Earth's oceans. One notable example is the Subsea project, which stands for Systematic Underwater Biogeochemical Science and Exploration Analog. This ambitious endeavor brought together scientists, engineers, and explorers to investigate volcanic activity at the Loihi Seamount, an active underwater volcano off the coast of Hawaii. The project aimed to study the unique chemical environment and the microbial life that thrives around these deep-sea hydrothermal vents. The Subsea team utilized remotely operated vehicles, or ROVs, equipped with a suite of scientific instruments. These robotic explorers could collect samples of water, rocks, and microbial life, as well as high-definition video footage of the vent systems. A key innovation tested during Subsea was a low-latency telepresence system. This allowed scientists on shore to participate in the mission in real time, guiding the ROV's movements and making decisions about sample collection. The findings from Subsea were illuminating. The project provided valuable data on the types of minerals and gases released by these underwater volcanoes and how they support microbial communities. It helped refine our understanding of the conditions that might foster life in similar environments on moons like Europa or Enceladus. Beyond subsea, NASA continues to be involved in various oceanographic research initiatives. These missions are not just about discovery. They are about building the knowledge base and technological capacity for future explorations, both on Earth and in the far reaches of our solar system. Exploring the ocean floor presents a formidable array of technological and environmental challenges. Perhaps the most immediate and daunting is the immense pressure. For every 10 meters of descent, the pressure increases by roughly 1 atmosphere. In the deepest parts of the ocean, like the Challenger deep in the Mariana Trench, pressures exceed 1,000 atmospheres. Any vehicle or instrument sent to these depths must be engineered to withstand such colossal forces without being crushed. Then there is the pervasive corrosive saltwater. Seawater is a harsh chemical environment, relentlessly attacking metals and other materials. Equipment deployed in the deep sea must be highly resistant to corrosion to ensure its longevity and reliability. The utter darkness of the abyss poses another significant hurdle. Beyond a few hundred meters, sunlight cannot penetrate, plunging the deep ocean into perpetual night. Exploration vehicles must carry their own powerful lighting systems to sea, but even the best lights can only illuminate a small area. Communication with surface vessels or shore-based control centers is complicated. Radio waves do not travel well through water, so acoustic modems are often used, but these have limited bandwidth. Scientists and engineers are increasingly focused on developing low-impact exploration techniques and adhering to strict protocols to minimize their footprint. The deep ocean, once thought to be a barren wasteland devoid of life, has revealed itself to be a surprisingly vibrant realm. The discovery of hydrothermal vents in the late 1970s revolutionized our understanding of where and how life can exist. These underwater volcanic hot springs spew out mineral-rich superheated water from beneath the Earth's crust. Around these oases of geothermal energy, entire ecosystems flourish, teeming with bizarre and wonderful creatures. Giant tube worms, blind crabs, and ghostly fish thrive in complete darkness, their existence dependent not on photosynthesis, but on chemosynthesis. This discovery was a profound moment for biology and astrobiology. It demonstrated that life could exist without sunlight, relying instead on chemical energy sources. This opened up the tantalizing possibility that life might exist in similar environments elsewhere in the solar system, such as beneath the icy shells of Jupiter's moon Europa or Saturn's Enceladus. The search for life in Earth's abyssal sanctuaries is not just about understanding our own planet. It is a direct dress rehearsal for seeking life beyond Earth. Scientists are particularly interested in extremophiles organisms that thrive in extreme environments. Studying their unique biochemistry, their genetic makeup, and the strategies they use to survive and reproduce in such harsh conditions provides crucial clues about the fundamental requirements for life. By pushing these boundaries on Earth, we can better define the habitable zones on other celestial bodies. The parallels between exploring Earth's deep oceans and searching for life on other planets are striking. Our planet's hidden watery realms serve as a natural laboratory, offering invaluable lessons for seeking life beyond Earth. The strategies and technologies in deep-sea exploration are often directly transferable to astrobiology. When we send a probe to Europa's subsurface ocean, it faces challenges like immense pressure and total darkness. Studying Earth's deep-sea hydrothermal vents provides a template for other ocean worlds. This knowledge helps identify promising locations to search for extraterrestrial life. The synergy between ocean and space exploration points towards an exciting future, filled with innovative crossovers and profound discoveries. Undersea environments are used for astronaut training. Imagine habitats on the sea floor for extended astronaut missions. These simulate isolation and life support systems for space missions. Underwater EVAs mimic microgravity for spacewalk training. Autonomous systems benefit both deep-sea and space exploration. Navigating robots in hazardous conditions is a shared challenge. AI and robotics for AUVs can benefit Mars rovers and space probes. Planetary exploration tech enhances deep-sea studies. The deep ocean promises new ecosystems and life forms. Each expedition could reveal unique organisms and biochemical processes. Discoveries expand biodiversity knowledge and offer new medical compounds. The convergence of ocean and space exploration leads to a holistic understanding of our universe. The deep ocean and the vast expanse of outer space, though seemingly disparate, share a powerful unifying characteristic. They represent the great unknown. They are frontiers that challenge our understanding, push the limits of our technology, and ignite our innate human curiosity. NASA's involvement in deep-sea exploration is a testament to this enduring spirit, a recognition that the quest for knowledge is not confined to a single domain but encompasses all realms where mystery resides. The challenges encountered in exploring these extreme environments act as powerful catalysts for technological advancement. The need to overcome these hurdles forces engineers and scientists to think creatively, to develop new materials, new systems, and new ways of operating. These innovations often have far-reaching benefits, spilling over into other fields and improving life on Earth in unexpected ways. Moreover, the search for life, whether in the hydrothermal vents of Earth's oceans or on distant planets, touches upon some of the most profound questions humanity can ask. What is life? How did it begin? Are we alone? These questions transcend scientific disciplines, engaging philosophers, artists, and every curious mind. Ultimately, the exploration of both inner and outer space is a journey of self-discovery. By venturing into the unknown, we learn more about our own capabilities, our limitations, and our place in the grand tapestry of existence.